Epistemic and doxastic logic are often treated as branches of modal logic concerned with reasoning about knowledge and belief. While classical logic focuses on what is true or false, epistemic logic studies what agents know, and doxastic logic studies what agents believe. These logics provide formal tools for analyzing concepts that are central to epistemology, philosophy of mind, philosophy of language, economics, game theory, artificial intelligence, and computer science, etc. Typical questions include: what does it mean to say that an agent knows or believes a proposition? How are knowledge and belief related? What logical principles govern rational belief and idealized knowledge? Epistemic logic typically uses operators such as K, meaning the agent knows that, while doxastic logic uses operators such as B, meaning the agent believes that. These operators allow us to represent informational states and reason formally about their structure. Multi-agent versions of these logics are especially important for analyzing communication, coordination, and strategic interaction between agents. The syntax of epistemic and doxastic logic extends classical propositional logic with modal operators for knowledge and belief. The basic vocabulary includes propositional variables, standard logical connectives, and epistemic or doxastic operators indexed to agents, such as K-A or B-A, where A denotes an agent. If C is a well-formed formula, then K-A, C, and B-A-C are also well-formed formulas. As in other modal logics, formulas are built recursively, and parentheses are used to avoid ambiguity. More expressive languages allow nested operators such as K, A, B, B, C, meaning that agent A knows that agent B believes C. These constructions are crucial for modeling higher-order knowledge and belief. The standard semantics for epistemic and doxastic logic is possible world semantics. A model consists of a set of possible worlds, an accessibility relation for each agent, and a valuation function. In epistemic logic, the accessibility relation is often interpreted as an epistemic indistinguishability relation. World V is accessible from W for agent A if and only if given what A knows at WV could be the actual world. In doxastic logic, the accessibility relation is often interpreted as a doxastic indistinguishability relation. World V is accessible from W for agent A if and only if, given what A believes, at WV could be the actual world. A formula K, A, C is true at a world W if and only if C is true at all worlds epistemically accessible to A from W. In doxastic logic, BAC is true at W if and only if C is true at all worlds doxastically accessible to A from W. The difference lies in the structural constraints imposed on the accessibility relations and in the informal interpretation of these relations. Knowledge is usually assumed to be factive and rational, whereas belief need not be. Different systems of epistemic and doxastic logic impose different axioms and semantic constraints. Here are some possible axioms. T in epistemic logic, K, A, C implies C. Knowledge implies truth. If A knows that C, then C is true. D in doxastic logic, B, A, C implies not B, A, not C. Belief is consistent. If A believes that C, then A does not believe that not C. 4 in epistemic logic, KAC implies KAKAC. If A knows that C, then A knows that A knows that C. 5 in epistemic logic, not K, AC implies K, A not K, AC. If A does not know that C, then A knows that A does not know that C. 4 in doxastic logic, sometimes called positive introspection. BAC implies BABAC. If A believes that C, then A believes that A believes that C. 5 in doxastic logic, sometimes called negative introspection. Not B, AC implies B, A not B, AC. If A does not believe that C, then A believes that A does not believe that C. Epistemic logic is often modeled by systems such as S4 or S5. System S5, for example, assumes that the accessibility relation is reflexive, transitive, and Euclidean, corresponding to the principles that knowledge implies truth and that every agent knows what she knows and what she does not know. Doxastic logic is often modeled by weaker systems, such as KD45, which assumes that belief is consistent and introspective, but not necessarily true. The axiom D ensures that agents do not believe contradictions, while axioms 4 and 5 capture positive and negative introspection. These differences reflect the intuitive distinction between knowledge as factive belief and belief as potentially mistaken. It is also possible to construct systems that combine epistemic and doxastic logic. In such systems, it is possible to discuss how knowledge and belief are related. Here are some possible axioms. K, A, C implies B, A, C. Knowledge implies belief. If A knows that C, then A believes that C. B, A, C implies K, A, B, A, C. If A believes that C, then A knows that A believes that C. Not B, A, C implies K, A, not B, A, C. If A does not believe that C, then A knows that A does not believe that C. Several proof methods are used in epistemic and doxastic logic. Axiomatic systems extend classical propositional logic with modal axioms governing knowledge or belief, and inference rules such as necessitation. Natural deduction systems provide rule-based frameworks that make reasoning steps explicit and intuitive. Semantic tableau and model-checking techniques are widely used in computer science and artificial intelligence, especially for multi-agent systems. Bi-simulation techniques are also important for comparing models and proving expressive equivalence. Each proof method offers different advantages depending on whether the goal is theoretical insight, computational efficiency, or practical implementation. One of the most discussed philosophical problems in epistemic and doxastic logic is the problem of logical omniscience. In standard systems, agents are treated as knowing or believing all logical consequences of their knowledge or beliefs. This idealization conflicts with the limited cognitive capacities of real agents. Several responses have been proposed. Some logicians develop weaker logics that restrict closure principles. Others introduce awareness models, impossible worlds, or resource-bounded logics to better capture realistic epistemic states. While these approaches sacrifice some elegance, they increase descriptive accuracy and practical relevance. Propositional epistemic and doxastic logic applies knowledge and belief operators to propositional formulas. Quantified epistemic and doxastic logic extends this framework by allowing quantification over individuals. This enables expressions such as everyone knows that someone is guilty, or there exists someone whom Alice believes to be trustworthy. Quantified systems are significantly more expressive but also more complex. They raise issues concerning quantifier scope, domain variation across worlds, and interactions between quantification and modality. These challenges mirror those found in quantified modal logic more generally. Epistemic and doxastic systems differ in their metalogical properties. Many propositional systems are sound and complete with respect to their semantics and are often decidable. Quantified systems typically lose decidability and may lack completeness. Multi-agent logics further increase complexity, especially when common knowledge operators are introduced. In epistemic and doxastic logic, a sentence is logically true if and only if it is true in all worlds, in all models, logically false if and only if it is false in all worlds, in all models, and logically contingent if and only if it is true in some world, in some model, and false in some world, in some model. Logical consequence is defined as truth preservation across all models as in modal logic, and an argument is valid if and only if the truth of its premises guarantees the truth of its conclusion in every world, in every model. Epistemic and doxastic logic offer useful formal frameworks for analyzing knowledge and belief. Although they rely on idealizations that raise philosophical concerns, they have proven important for understanding, for example, rational agency, communication, and information flow. As a result, they remain central tools in both philosophical logic and its many applications,